Okay, I think we're live. So one of the earliest applications of calculus were mathematicians that were desperate to know values like sine of pi over 8, let's say. Like there's certain values of sine that are nice and easy and they're integers, or you can use a right triangle trig to get them. But sine of pi over 8, this is a transcendental number. It's not rational, and you can't solve it with a polynomial. Like rational numbers, you can always solve with polynomials. Natural log, a lot of values you can't get. And so this was actually one of the first applications of calculus, what we're going to learn today. This is what your calculators do. And it's very beautiful, I think. I think this is really nice math. You have to know a lot of math to get here. But you guys do, and you guys can do this. So if I explain it well, there's a lot of pressure on me to do it today to explain it well, I think we'll be good. So this is, what we're going to study today are called Taylor series. So you guys learn power series. So now what we're going to do is we're going to take a power series and we're going to alter a little bit. So here's a power series, just the straight up x to the n. You guys worked with that last night in your homework, correct? So you know that it's a geometric series. And if x is between -1 and 1, you know it has a singular value that we can find. And that is, the sum is 1 over 1 minus br, or 1 minus x. And so the crazy thing is, if you think about it, you can equate a series to a function. This function being f of x equals 1 over 1 minus x on the contingency that the absolute value of x is less than 1. Those things are equal. This infinite polynomial matches with a function. So now this notation, we're going to say the polynomial of x is the series generated by this. The function of x is generated by this. These two are equal. So that got people thinking, wow, if this is true, then why can't we use polynomials to approximate values of sine and of e? And they did it in a very cool way, and I think you guys are going to like this. So our goal, given a function and a point on the x-axis, find a polynomial that best approximates the function f of x in the vicinity of the point A. So if we think of sine, let's say we know that point. So what if I want to know a point just a little bit like pi over 12, just a little bit to the right? Well, if I can get a polynomial to approximate values in this little section, right in here, I can approximate pi over 15 or pi over 12. But the polynomial, it's going to be something that is close to the value in here, not out further, because it's not going to behave like this sine wave forever. But can you imagine that I can make a polynomial that kind of looks like this? You can have a polynomial that kind of looks like that, can't you? We saw that when we were doing derivatives. It's not that unreasonable that we can make a polynomial for it to look like that, and this is the steps to do it. Any questions about that? All right, so now that's the concept, and here's the mechanics of it. And the mechanics is not too hard. And Alex, do you mind pushing up the screen? So I want this at the top, the polynomial. Okay, thank you, perfect. That's great. So we're going to start with an easy example. F of x equals e to the x. It's not easy in a lot of ways, but it's easy to take the derivative of e to the x, isn't it? So here's my polynomial, my power series. And it's got some coefficient generated by that a sub n, and then my x squared, x cubed, x fourth, blah, blah, blah. So how do we find the values of the coefficient? Well, we're going to force a match between p of x and this f of x. Here's my polynomial. I did it with a geometric series. I'm going to do it with this. So if I let x equal to 0, someone got this great idea. If I let x equal to 0, all these cancel, don't they? And then I can just find the value of that c sub 0, c sub 0. So what if I plug in 0 for x here and 0 for x here, and then set these two equal? That's forcing a match so that I can find the value. Whatever f of 0 equals, I'm going to make p of 0 have that same value. So this is really the only nice value of e I can find, because that's just 1. So if I plug in 0 for here, I get this coefficient plus 0, plus 0, plus 0, plus 0. So I'm going to say when x is 0, make these two equal. So force the match. C0 equals 1. So that's true. When x is 0, now my polynomial for the first term is exactly the same as my function. You guys agree with that? But now, how am I going to find that C1 with an x? Well, this is where calculus comes in. When you take the derivative, the constant goes away. And then this x goes away. So if I take the derivative here, I lose this first term, and then I'm going to lose that x. And all of these x's go away. So someone just noticed, it's really handy that when you take the derivative of x, you get 1. So here we go. We're going to take the derivative of the function, take the derivative of the polynomial, and then force the match again. And that will tell me my c sub 1 value. So here I go. It's so handy with e to the x because the derivatives are still always the same. So when I plug in f prime of 0, I still get 1. I'm going to get it every time. So now I'm going to force the match. So now I have p prime of 0 equals this c0 went away, and then I have c1 plus, oh, that's gone, 0, dot, dot, dot. Good? So now, we're going to set these two equal. See, this is supposed to be a 0. It's hard to read because I'm a sloppy pen, but C1 equals 1 also. But now the 1 business is going to stop. We'll see what happens next. Hey, Alex, can you mind pushing that up? I want this, sorry, I want F double prime. Thank you. Because now, when I took the derivative of this, now I have a squared here, and that comes forward. As a matter of fact, to see the pattern that's happening here, if I take x to the 4th is my function, and I take the first derivative, I get 4x to the 3rd. I take the second derivative, what do I get, guys? 4 times 3x squared. If I take the third derivative, what do I get? 4 times 3 times 2x. Isn't that 4 factorial? Yeah. You see, I'm going to keep taking the derivatives, and the higher the exponent, well, that exponent is going to be, it's going to be 5x to the 4th, then 5 times 4x to the 3rd, 5 times 4 times x times 3 times x squared. So you have already seen the summation notation for e. And you're like, what? E to the x can be put equal to a series. And if you remember, it was n factorial was part of that. You're going to derive it today. So now, keeping that in mind, we take the third derivative. Second derivative. Here we are. This I can just keep rewriting. It doesn't matter. And because for these Maclaurin and these Taylor series, we take so many derivatives, sometimes you'll just see f2 as a very special notation, meaning the second derivative of f. Because we have to take 3rd, 4th, 5th, 6th, 7th, 8th, and writing dashes gets really tedious. So this is still 1. And now, here's where things start to change. So I'm going to say p double prime 0 equals this plus 0, plus 0, plus 0, plus 0. So now that coefficient is going to come into play when I'm looking for the value of this. So here I go. I set them equal. I'm forcing the match. 1 equals 2 c sub 2. So c sub 2 actually equals a half. So far I have 1x plus 1/2 x squared. for my polynomial. Questions, guys? All right. And Alex, you got a big job today. You got to flip the paper and, yeah, thank you. Can I have the top? Whee, getting dizzy. So dizzy. All right, good. So now, so what I just want you guys to do here is to say, when I plug in 0 here, I got this. And then when I force the match, I set it equal to the function at 1, and I got this is equal to 1. Here, I got C1. Here, I got double prime of 0, and I got 2C2. And here, triple prime, I get 3 times 2C sub 3, etc. So you guys see this factorial pattern happening. Yeah? So now, what we're going to say here is this is actually, when we have f to the nth derivative, we're getting n factorial c sub n. What does this mean? It means if I want to know the 6th coefficient, f6 of 0 is going to be set equal to 6 factorial c6. I know that's 1 because e to the x is always, the derivative is always e to the x, and when I plug in 0, I always get 1. So c sub 6 is 1 over 6 factorial. Well, I guess I could do it here, but equals n factorial c sub n. And then when we solve, we get 1 over n factorial. So now let's build our polynomial with this pattern, knowing this rule. So remember, it's CO plus C1 x1 plus C sub 2 x2 plus C3 x3 plus dot 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 dot. So what was C naught? Do you guys remember what it was when we did it on the previous page? 1. What was this one? 1x. What's this one? Yep. And I'm going to do it x squared over 2 factorial. You don't have to do that, but just to show you the pattern, plus x cubed over 3 factorial plus x to the 4th over 4 factorial plus dot dot dot. Ta-da! A polynomial that approximates e to the x, for real.
For how long does it hold for?
So remember, we centered this at 0. So what does that mean? That's a great question, Meredith. So here is our e to the x graph. So this polynomial, because I kept plugging in x equals to 0, remember I did that?
Yeah.
So that means I'm limited to the area around here, this region. This is where I'm going to approximate it well.
Okay.
If I want to go out, I have to start adding many, many, many terms.
What's the radius?
The first term is the same as e to the 0. That's the same. What's that question?
What's the radius?
So we're actually gonna do that. Very good. So that's delayed. We're gonna delay that for a little bit though. But what we're gonna talk about is how close do we get to the real value?
It's going to be less accurate the further it goes. It's
Yes.
not like there's a fence after.
Oh, there's.
Yeah, exactly. This is going to converge because we have x to the n over n factorial. N factorial always wins. So this converges to this. But as we go out, just like Jonah said, as we go out, our approximations get worse and worse. Unless, so like if I want to say, well, what's e to the 6th using this, it'll be okay. Not great. I have to add more terms. You have to generate more terms. And I'll show you an example of that later. So, from those questions, I think you guys are good. This is actually, I told you like the mechanics aren't that complicated, but it's a big concept. So Alex, do you mind pushing that up a little bit? So I did a lot of these notes for you. So here's a formal definition of the Maclaurin polynomial. And you see this notation, so we have f of 0 plus f prime 0 x. Dot, 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 dot. This should have a dot, dot, dot at the end. Dot, dot, dot. So now, with that being said, you guys are going to do your own one here. We're going to do it for sine. We're going to find the Maclaurin series for sine. And on your homework tonight, I think it's really helpful to make a chart that works for me. Because the first thing I have to do is I have to take the derivative of my function, my transcendental function. So I like to make my first column be the function derivative. And then my second column is the value for that, for f prime, f double prime, whatever, at where I'm centering the polynomial. So you take this, and you're going to plug in 0. For this case, we're going to center it at 0. And then, once I have this value, then I take that value and divide it by n factorial. That's coming from the derivatives, right? You do like the 5th power times 5 times 4 times. So we're going to divide, take this, and then you're going to divide by n. That's the piece you do here. This you just plug in. And then finally, the last column is when you're going to add your x to the nth term. And then we assemble this column to be our polynomial. Now, can you do this in your head? Maybe I can't, so I have to do a chart. But I'm going to do this quietly up here. I want you guys to do it quietly in your tables. Okay? You guys about done? Yeah, so what happened with the even values is that we got zeros, the even powers. So when I assemble my polynomial, the notation is p of x. This is f of x. This is polynomial of x. And we just do x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. You see the pattern. Minus x to the 7th over 7 factorial plus dot, dot, dot. Now, there's a funny notation here. If I want to approximate sine, and I use these 4 terms, I'm going to sum up these 4 terms. You guys knew that this is the notation for summing up 4 terms of a series. For Taylor polynomials, what they do is they say, how far did you get with degrees? So the subnote here is actually the highest degree of your term, the degree of your highest term. So that's saying, do this until you get this to the 7th degree Taylor polynomial, which is actually only 1, 2, 3, 4 terms. So you'll see that in your book. P sub 7 of x, 7th degree. Now, does this make sense to us? What kind of function, odd, even, or neither, is sine? Odd. Does it make sense that only the odd values are here? 1, 3, 5, 7. If we're going to model an odd function with a polynomial, it better be an odd polynomial.
I guess.
Yeah, it will be. So that's one way to remember. This, you guys just on your own derived the Maclaurin series for sine. Now keep in mind though, this is centered at 0, so it's for values around here.
Are we going to center it and go to 0?
Yeah, that's the next example. So questions? Yeah, Aiden.
So could you use that bottom bit there to find the sum?
You could. And as a matter of fact, I want you guys to do that on the next part of your packet. So, and Alex, you're so sad you sat there today.
Yeah,
But aren't you guys glad I typed this all up for you?
Yeah.
It just makes the lesson go a lot faster. So, so now obviously we don't need a Maclaurin series to find sine pi over 4 because we can use 45, 45, 90 triangle, pi over 4, pi over 4, pi over 2. But let's just do it. I want you guys to take out your calculator, and you know that this is root 2 over 2. I want you to sum these up using your calculator. So I think maybe the easiest way to do it is to do x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, and either put it into your y equals and use the table function, or you can just assign x a value. You can do you can do pi over 4 store x and then hit enter. So please type this in, p7 of x, and then tell me what you get when you let x be pi over 4. This is what your calculator is doing. It's saying, I have this memorized. Give me my x. You have a choice. I think the easiest way is to go into your y1 and type x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. And then
doing what? Oh, and then just, wait, then doing what?
And then go to the table.
Go to the table.
Yeah, and just do enter.
That's pretty close.
Pretty close, right? So this is 1, 2, 3, 4, 5, 6, 7, 8 decimal accuracy. That's according to my calculator, which is using the Maclaurin series. But yeah, but so what'd you already got it, Jonah? That was fast. What'd you get?
107, 106.
Did you really?
Yeah.
Wow.
Yeah.
So I didn't use my calculator. I used a more powerful program online to get that. So I think that's probably a little more accurate. But yeah, so it really, really does work. So I interchanged Maclaurin series and Taylor series. So Maclaurin series, they're a specific kind of, it's a subset of a Taylor polynomial. Centered at x equals 0, centered at a equals 0. So Maclaurin series is a Taylor polynomial centered at a equals 0. They're both Taylor series.
Wait, so what's s sub 3x?
So these are different. This is saying add up that, and that. The first three terms. This equals
And that
x
one says
minus x cubed over 3 factorial plus x to the 5th over 5 factorial.
first 3 terms as opposed to until the
Yeah, and this one is different. This is just x minus x cubed over 3 factorial. So this p sub 3 means 2 terms. This 3 actually means 3 terms. It's a little confusing if you're not mindful of that on your homework tonight.
Isn't that fun because there are zeros in between those terms?
What's that?
There are zeros in between the terms. Like, shouldn't they be the same thing? Like, you're just dropping the zeros, but they are there.
Yeah, that's good. That's interesting. Yeah, this would be, we had 2 zeros, but this one has more zeros. Is this had a 0 here, 0 here, 0 here? Maybe I don't answer your question, but can you put it on hold and I'll
It doesn't really matter.
okay, sorry. So now we're going to do a Taylor series that's not centered at 0, and then I'm actually on with the lesson. So it's not much different. Alex, you mind pushing that up?
Of course. I don't mind.
Thank you.
Good.
So perfect. So you see the same thing happens. We have this C0, C1, C2, C3, C4. But now it's just a shift, just like you guys know with a parabola that's like x squared, x minus 2. You know, if we have a parabola, y equals x squared is our parent graph, y equals x minus 2 is a shift to the right. Well, that's the same that's going on here. We're shifting it over a, and that's to make it more accurate. If I want to know, let's say I want to know sine of pi over, I don't know, 9. I wouldn't want to use sine of 0 because I can find exact values for pi over 6 or pi over 3 or pi over 4. So I'd want to center it closer to this. However,
So does your calculator also figure out how close it wants to center it, as well as?
so what your calculator does is it says, I'm going to use quadrant 1 angles only, and then I'll do reference angles for the rest. So that's what it's doing.
But it still doesn't.
So it's between 0 and pi over 2, but it uses a lot of terms. So it's really accurate.
It centers it at 0.
Yeah, it's 0. So now we're going to do a Taylor series for the natural log of x, centered at a equals 1. So can you push this up a little bit? I think you guys can do this by yourselves. I think so. I'll do it quietly up here. It's the same. It's just this last step. We're going to have to introduce this x minus 1 to the n power instead of just x to the n power. What's the derivative of natural log? 1 over x, but use x to the negative 1. Okay? And you see we're going to create an alternating series like we did last time with sine. So something kind of crazy happens with this one. Yeah, the factorial is kind of canceling. Because we're doing a factorial here, but it's one step behind. So where the factorials are kind of canceling out. So now we have to put in our x minus 1 term. We don't have this one, so we have this. Where this is the degree that I'm in. So I go across, this is x minus 1. And then here, negative 1/2, the x minus 1 squared, 1/3, 3. So here I'm going to do, let's just do P4 of x. X minus 1 minus 1/2 minus 1 squared plus 1/3 x minus 1 cubed minus, and I'm going to stop at degree 4. And
Oh, I see what you're saying.
I think I'm going to stop there for now. So I'm going to turn off this. That was okay, guys? Oh, thank you. Man, nice.